Hi everyone, welcome back to another video of chemical bonding, that is molecular orbital theory, and this video is probably the last video of this session, molecular orbital theory, because so far in too many videos we have discussed about valence bond theory, molecular orbital theory, and that of different systems for up to 14 electron system and more than 14 electron system. And in this video we are going to discuss the molecular orbital diagram for heteronuclear diatomic molecules such as carbon monoxide, nitric oxide, etc. So far we have been discussing the MO diagrams of homonuclear diatomic molecules such as hydrogen molecule, nitrogen molecule, etc. So their homonuclear diatomic means we know both the atoms are same. Whereas in this case the atoms are different, that is heteronuclear diatomic molecule. And also we are discussing the comparison of stability, bond length, etc. of different species. We have been seeing so many molecules. Now let's compare all these based on their bond order value. Let's compare their bond dissociation energy, bond length, etc. from the bond order value. So that is the essence of this video we are going to discuss. Let's see heteronuclear diatomic molecules. First of all, carbon monoxide. The MO diagram for MO configuration of homonuclear and heteronuclear diatomic molecules are similar because it just depends on the number of electrons, total number of electrons present. And we know carbon monoxide molecule, carbon atom has 6 electron, oxygen atom has 8 electron. So it has total 14 electron. So carbon monoxide is a 14 electron system, or we can say it is isoelectronic with nitrogen molecule. We know nitrogen molecule also has 14 electrons. So this MO configuration of carbon monoxide is same as that of MO configuration of nitrogen. That is, for up to 14 electron we have the rule sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 equals pi 2py2, sigma 2p z2. 2, 4, 6, 8, 10, 12, 14. So, MO configuration of carbon monoxide is same as that of nitrogen, and so bond order, everything will be same as that of nitrogen. Half into number of electrons in bonding molecular orbital to that in anti-bonding, that is half into, we have 10 electrons in bonding, that is 2, 4, 6, 8, 10, 10 minus 4 electrons in anti-bonding, 2, 4. So bond order is 3. That means there is a triple bond connecting carbon and oxygen atoms. But even though the MO configuration is same, their MO diagram is not similar, not exactly similar. Some similarities are there, but there are some differences as well. So let's see what are the differences in the MO diagram of carbon monoxide and nitrogen molecule. First of all, as in the case of any MO diagram, we have to show the energy, and down we are representing the atoms. Atom labels has to be there. So I am writing carbon on one side, oxygen on other side. Usually for nitrogen molecule, we know the atomic orbitals, say 1s and 1s, they are drawn on the same line because both are of same atom and their energies are same. But here in this case, one is carbon and other is oxygen. So the atomic orbital, 1s of carbon and 1s of oxygen have different energies. And we should know which is having lower energy compared to the other. Always the more electronegative element will have slightly lower energy atomic orbitals. That is, if we take the 1s atomic orbital of carbon and oxygen, the oxygen atomic orbital will be slightly lower in energy compared to carbon. That is, the same 1s will be of lower energy for the more electronegative element compared to less electronegative element. So that is one of the main differences in the MO diagram for homonuclear and heteronuclear diatomic molecule. And we know both 1s of carbon and oxygen contain 2 electrons. So their bonding and anti-bonding, sigma 1s2 and sigma star 1s2. From this we can see, since the oxygen atomic orbital is of lower energy, always the bonding molecular orbital will be more close to the more electronegative element atom, and the anti-bonding molecular orbital is more close to the less electronegative atom. That is because of the difference in the energies of atomic orbitals. Their bonding orbital and anti-bonding orbitals are not equidistant from the corresponding atomic orbital. This is in contrast to the homonuclear diatomic case, because in that case we know the bonding orbital and anti-bonding orbitals were equally spaced from the respective atomic orbitals, whereas in this case, since oxygen atomic orbital is having lower energy, always the bonding orbitals are more close towards the oxygen atomic orbital, and anti-bonding orbitals are more close to the less electronegative elements atomic orbital. So close in the sense, we can say in other words, the bonding molecular orbital electrons, the electrons present in the bonding orbital have more characteristics of oxygen, while the electrons in the anti-bonding orbitals have more characteristics of carbon. So that is the difference. In the case of homonuclear diatomic molecule, the electrons in all the molecular orbitals have equal characteristics from both the atoms, but here it is not so. And in the same way, for 2s, when we draw the 2s atomic orbital, then also we have to show that slight change in energy. Oxygen is slightly lower in energy. Okay, when we draw the diagram, it has to be lower in energy. So we can draw the sigma 2s and sigma star 2s. There are also 2 electrons, sigma 2s2 and sigma star 2s2. Then we have the p orbitals. When we draw the p orbital, the atomic configuration is different on either side. We know there are 3 orbitals in the p subshell, and for carbon the configuration of 2p is 2p2, while for oxygen the configuration is 2p4. So that is also another difference in the atomic orbital configuration. For homonuclear diatomic, on either side the atomic configurations are same, but here it is not so, and they combine to give the bonding, 3 bonding orbitals, that is pi 2px equals pi 2py, sigma 2pz, pi star 2px equals pi star 2py, and finally sigma star 2pz. So the electrons count, electrons filling, we know 2 plus 4, 6 electrons are there, and we know the MO configuration also. We have pi 2px2, pi 2py2 and sigma 2pz2. The anti-bonding from 2p remains vacant. So this is the MO diagram for carbon monoxide molecule, and we can see the main differences between the homonuclear and heteronuclear MO diagram is that one thing, we have on either side different atoms, so their energies are not on the same line, energies are slightly different, and always the more electronegative element will have lower energy than the less electronegative element. And also another difference is in the atomic orbital configuration, especially in the valence shell. We have for carbon 2p2 configuration and for oxygen 2p4 configuration, but once they combine to give molecular orbitals, their configuration is same as that of a homonuclear diatomic molecule. The total number of electrons only matters. Okay, so this is the MO diagram for carbon monoxide molecule, which is slightly different from that of nitrogen molecule. So that was the MO diagram for carbon monoxide molecule. In the same way, we can draw MO diagram for NO, nitric oxide molecule. In the case of NO, we know nitrogen atom has 7 electrons, oxygen atom has 8 electrons. So total number of electrons is 15 and their MO configuration is, we know it is 15 electrons. So more than 14 electron, we have to see the second role, that is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then comes sigma 2pz2. Then we have pi 2px2 equals pi 2py2. Then pi star 2px equals pi star 2py. You have to count the number of electrons: 2, 4, 6, 8, 12, 10, 12, 14. One more electron is there, so that goes to pi star. Both are of same energy, so the remaining one electron goes to any of the pi star orbital. And here we know number of electrons in bonding orbital is 2, 4, 6, 8 and 10. And number of electrons in anti-bonding orbital 2, 4 and 5. So bond order equals half into 10 minus 5, that is 2.5. 5 by 2, 2.5. So here the bond order is a fractional value. That means it is intermediate between double bond and a triple bond. It is having intermediate character between double and triple bond. Now let's see the MO diagram of nitric oxide molecule, which is almost similar to the MO diagram of carbon monoxide, which we have already seen. We have to show the energy. Nitrogen on one side, oxygen on another side. We know oxygen atomic orbitals are slightly lower in energy. So their 1s combined by addition to give sigma 1s and sigma star 1s. The same way 2s combined by addition to give sigma 2s and by subtraction to give sigma star 2s. So we can fill the electrons also. Then we have 2p. We know oxygen is more electronegative. So its energy level should be shown slightly lower. And first we have sigma 2pz. Since it is more than 14 electron system, the sigma 2pz should be of lower energy. Then only pi 2px and pi 2py. Then we have pi star 2px and pi star 2py. And finally sigma star 2pz. So the electron, we know nitrogen, it is 2p3 configuration, whereas oxygen is of 2p4 configuration. So the total number of electrons in the molecular orbital will be sigma 2pz2, pi 2px2, pi 2py2, pi star 2px1. So this is the MO diagram for nitric oxide molecule, which is almost similar to carbon monoxide because both are heteronuclear diatomic molecule. But when we compare in carbon monoxide, the electrons were filled up to the sigma 2pz. We have pi 2px and pi 2py lower energy. then sigma 2pz. So here one additional electron. Carbon monoxide was 14 electron, here it is 15 electron. So the 15th electron is going to the anti-bonding orbital, that is of destabilizing nature. That is why our bond order decreases. We know if we have more electrons in the bonding molecular orbital, that will be stabilizing and it will have higher bond order, whereas if the anti-bonding orbital have more electrons, it will be destabilizing in nature, so resulting in a decrease in the bond order value. So this additional electron in the anti-bonding results in a decrease in bond order compared to carbon monoxide molecule. So this is the MO diagram for nitric oxide, NO. So we have now discussed the molecular orbital diagrams for different molecules such as homonuclear diatomic molecules and heteronuclear diatomic molecules. Now let's have a comparison of the bond order and the bond dissociation energy, stability, bond length, etc. of different molecules or different species. So I have given here a number of species and let's see how their bond order will be changed and consequently how their bond dissociation energy, bond length, etc. varies. We know for nitrogen molecule we have seen the configuration sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px equal to pi 2py2, 2 each. Then sigma 2pz2. This is the configuration for nitrogen molecule and we know the bond order is half into number of electrons in bonding comes out to be 10 and the number of electrons in anti-bonding is 4. So resulting in a bond order of 3. Okay, so this is the case of nitrogen molecule. When we take oxygen molecule, the difference comes after sigma star 2s. That is after sigma star 2s we have sigma 2pz2, then pi 2px2 equals pi 2py2, pi star 2px1 equals pi star 2py1, because we know oxygen molecule has 16 electron, nitrogen is 14 electron, here it is 16 electron, more than 14 electron. So this is the rule and its bond order comes out to be half into number of electrons in bonding is 2, 4, 6, 8, 10, 10 minus number of electrons in anti-bonding 2, 4, 5 and 6. So bond order comes out to be 2. So for nitrogen it is 3, oxygen 2. Now let's take O2 plus. O2 plus means the number of electron will be 15. 1 electron will be lost from oxygen molecule. So it is 15 electron. So since 1 electron is lost, we know it is from the highest energy pi star. It is from one of the anti-bonding pi star. And it is clear, even without calculating the bond order, we can predict. That is the electron. Now the electron, one of the electron from the anti-bonding orbital is removed, or we can say it results in a stabilizing. Now anti-bonding electrons has reduced. So it becomes 10 minus 5. Bond order is equal to half into 10 minus 5. Number of electrons in anti-bonding orbital is 5. So it is 2.5. Bond order comes out to be 2.5 for O2 plus. Okay. Now O2 2 plus. O2 2 plus means it is 14 electron system. Okay. 2 electrons are lost from oxygen molecule. So the total number of electrons now become 14. So 14 means the configuration itself will be changed. The configuration will become sigma star 2s2. Then we have pi 2px2 equal to pi 2py2. Then sigma 2pz2. That means its configuration is same as that of nitrogen. So bond order will be same as that of nitrogen, that is 3. We have already calculated bond order for nitrogen. So for O2 2 plus, since it is isoelectronic with nitrogen, bond order is 3. And for O2 minus, O2 minus means we know again we have oxygen 16 electron, one more electron is added, so 17 electron. So the configuration will be sigma 2p Z2 pi 2p x2 equals pi 2p y2, pi star 2p x equals pi star 2p y. For O2 this was the configuration, and O2 minus means it becomes pi star 2p x2 equal pi star 2p y1. That means one additional electron has gone to the anti-bonding molecular orbital, and we know it will be destabilizing. Okay. So bond order become half into 10 minus. For the case of oxygen it was 10 minus 6. So 4 by 2, but here it will be 10 minus 7 because one more electron is there in the anti-bonding. So we have 2, 4, 6 and 7. So the bond order will be 3 by 2, 1.5. So compared to oxygen, the bond order has reduced for O2 minus. And for O2 2 minus, we know it is 18 electron, 16 plus 2 extra electron, so it is 18 electron, and the configuration will be pi star 2p x2 equals pi star 2p y2. So again antibonding electron increases and bond order become 2 by 2, that is 1. So bond order still decreases. And nitric oxide we know it is having 15 electrons, nitrogen 7 and oxygen 8, 15 electron system. So 15 electron system means it is isoelectronic with O2 plus. O2 is 16, O2 plus is 15. So O2 plus is having a bond order 2.5. Okay, similarly cyanide ion, we know carbon is having 6 electron, nitrogen is having 7 electron plus additional 1 electron. So it will be 14 electron. So cyanide is also isoelectronic with nitrogen. So it will have a bond order 3. So we can compile all these. So we get for nitrogen bond order is 3. For O2 it is 2. O2 plus, we can write it in the order. That is, first we can write O2 2 plus, that is isoelectronic with nitrogen. So 3 bond order. Then O2 plus means bond order become less, 2.5. Then we have O2 bond order 2, O2 minus 1.5, O2 2 minus 1. Then we have nitric oxide which is isoelectronic with O2 plus. So that is having 2.5, and Cn minus is isoelectronic with nitrogen. It is having a bond order 3. So this way we can compare the stability, bond dissociation energy, etc. We know nitrogen, O2 2 plus, Cn minus, these are having the highest bond order. Then comes O2 plus, NO, they are having 2.5 bond order. Then we have O2 with bond order 2, then O2 minus with bond order 1.5, and finally O2 2 minus with bond order 1. So with this way we can compare, like higher the bond order value, higher will be the stability and higher will be the bond dissociation energy, and also lowest will be the bond length. We know bond order is directly proportional to bond dissociation energy and inversely proportional to bond length. So this way we can compare any number of molecules. If we know the molecular orbital configuration, we can predict their relative stability, bond dissociation energy, bond length, etc. So these are the main this way we can compare different species based on molecular orbital theory. Hence, in conclusion, we have discussed the MO diagram for different heteronuclear diatomic molecules. That is in contrast to homonuclear diatomic molecule. Here the differences we have seen. Differences in the atomic orbital energies and also the atomic orbital configuration. But the MO configuration remains same in homonuclear and heteronuclear diatomic molecules. And we have seen the diagram for carbon monoxide and nitric oxide molecule. And also we have compared the bond order, bond dissociation energy, etc. or different species such as O2, O2 plus, O2, 2 plus, O2 minus, then Cn minus, etc. So these are the main essence of molecular orbital theory. We have seen the molecular orbital concept, MO configuration, bond order calculation, MO diagrams of different systems. Okay, so this with this I hope the molecular orbital theory main parts is finished, and in the next video we can discuss about hybridization and VSEPR theory describing molecular geometry. So hope you all understood this video. Thank you all.